In this lesson, you will learn what are the primary functional components of an electrochemical cell and what are their functional purposes. I will make a distinction in this specialization between what I'm going to call an electrochemical battery cell and what I will call a lithium-ion battery cell. Both of these are considered battery cells, but they work on somewhat different principles. And this week we're going to study electrochemical cells and how they work. Next week we will turn our attention instead to looking at how lithium-ion cells work a little differently. The focus of the specialization, of course, is on algorithms for managing lithium-ion cells, so we need to learn how they work. And fortunately, lithium-ion cells operate on many of the same basic principles as for electrochemical cells. So what you're going to learn about this week is still really foundationally important for understanding how lithium-ion battery cells work also. In particular, lithium-ion cells have all of the component parts that you're going to learn about in this lecture topic. And again, next week our focus will shift to understanding lithium-ion battery cells in more detail. On this slide, I have included a drawing that you will see many times in the specialization that depicts a cross-sectional view of the internals to a battery cell. To the left of the drawing, the negative electrode is shown as a collection of green shapes, and to the right of the drawing, the positive electrode is shown as a collection of purple shapes. And throughout the illustration, you will see a light blue color in between these shapes that illustrates the electrolyte. In between the negative electrode and the positive electrode is something called a separator. And finally, on the edges of both sides of the illustration, you can see thin rectangles, on one side orange and on the other side gray, that depict the current collectors. The colors that I have used in this illustration are for illustrative purposes only. If you were to open up a battery cell, which by the way is not recommended because often they contain chemicals that can be toxic, but if you were to open up a battery cell, you would see that the compounds are usually black or gray. They're usually quite colorless. So I use these colors on the diagram simply for illustration, but I will use the same color scheme throughout the specialization. So whenever you see an electrode that's colored green, that will be a negative electrode. Whenever you see an electrode that's colored purple, that will be a positive electrode. Whenever you see a current collector that's colored orange, that will be a negative electrode current collector. And finally, whenever you see a current collector that's colored gray, that will be a positive electrode current collector. Over the next several slides, I'm going to go into more detail regarding what each of these components is and what its function is. But before we move on, I should mention that the diagram on this slide corresponds most directly to what you would see if you were to open up a lithium-ion battery cell. Some electrochemical cells have similar physical structure, but some of them also have quite different structure. But even so, regardless of the internal structure, all battery cells of whatever variety are going to have a negative electrode and a positive electrode and separators and so forth. Battery cells operate by moving charge between their negative and positive electrodes. So you can think of the electrodes as being charge storage reservoirs. In a regular electrochemical cell, the negative electrode is often constructed from a metal or an alloy of metals or even hydrogen itself. In a lead-acid battery cell, for example, the negative electrode is some kind of a lead metal or lead paste. And by the way, I think this is the first time I've shown you the acronym PBA for lead acid. The PB is the chemical symbol for lead from the periodic table, and A simply stands for acid. During a battery cell's discharge process, the negative electrode gives up electrons to the external circuit. It provides electrons to the external circuit. Technically, we say that the negative electrode is oxidized in this process. Oxidization is a process where a compound gives up electrons. So electrons are lost from the electrode, and if you want to remember what happens to electrons during oxidization, it's helpful to remember the acronym OIL. OIL stands for oxidization is loss of electrons. During a battery cell's charge process, exactly the opposite thing happens. The negative electrode accepts electrons from the external circuit. In fact, these electrons are forced into the negative electrode by applying a higher external voltage to the battery terminals than the battery itself wants to deliver. And that places an external electrical pressure on the battery cell that forces the electrons into the negative electrode. We say that the negative electrode is reduced as the battery cell is charged. Again, if you want a helpful acronym to remember this, think of the acronym RIG. RIG stands for reduction is gain of electrons. So together we have two acronyms, oil rig, and I find that quite humorous myself because we're talking about a subject in this specialization that's supposed to be very environmentally friendly and green, but we remember how everything works by thinking of oil rig, which most people would say is not a very environmentally friendly subject at all. During discharge of the battery cell, when the negative electrode is giving up electrons, the negative electrode is also technically known as the anode of the battery. The anode is the electrode where chemical reaction produces extra electrons. However, during charge, the negative electrode consumes electrons, so during charge, the negative electrode is technically the cathode. And so it's very confusing to change your terminology, referring to as fixed, specific physical part of the battery cell, and to say that it's the anode during discharge and it's the cathode during charge. So most people still refer to the negative electrode as the anode even during charge. But I would like to be as precise as possible to avoid as much confusion as possible, I hope, in this specialization. So I tend to avoid terms like anode and cathode. Once in a while you may hear me slip up and the terms may come into my speech, but I try to instead use the terms negative electrode and positive electrode, even though it's a little longer to say, a little bit more cumbersome. But you should be aware when you look at the literature that when people talk about anode, they are most often talking about negative electrode, and when they talk about cathode, they are most often talking about the positive electrode. And this will help you connect what I teach in the specialization and what you learn here to what you read in the literature as well. So now let's turn our attention to looking at the positive electrode of an electrochemical cell. In a standard electrochemical cell, the positive electrode is often some kind of a metallic oxide or a sulfide or even in some cases oxygen. In a lead-acid battery cell, the positive electrode is made from lead oxide. During the discharge process, the positive electrode accepts the electrons from the external circuit, and since it's gaining electrons, we say that the positive electrode is reduced. Remember, reduction is gain. During the charge process, on the other hand, the positive electrode is forced to give up electrons to the external circuit, and so the positive electrode is oxidized. Remember, oxidization is loss of electrons. During discharge of the battery cell, the positive electrode is called the cathode because it's the electrode being reduced. The cathode, remember, is the electrode where reduction is happening. So technically, during charge, the positive electrode is really the anode because it's being reduced at that time. Again, this is confusing to refer to the same physical electrode as the cathode one time and the anode another time. So most people refer to the positive electrode as the cathode even during charge. Again, I bring this up mostly so you will have a level of comfort when you read the literature and you see the term cathode in some article, and you will understand that the authors are almost certainly referring to the positive electrode of the battery cell. And again, to be as precise as possible and hopefully to avoid confusion, I will refer to this part of the battery cell as the positive electrode and not usually as the cathode. I've talked a little about how electrons are sourced in one of the electrodes and consumed by the other electrode during charge and discharge, and how electrons flow in the circuit external to the cell from one electrode to the other, but we have not talked yet about what happens internal to the cell while this is happening. In fact, locally, we need to have a charge balance. So if we're giving up electrons, then we would tend to have a local net positive charge that somehow must be balanced by a net negative charge internal to this cell in the neighborhood of that location. And this is done by charged particles known as ions that are moving around inside of the battery cell. An ion with a net positive charge is called a cation, and during discharge of the battery cell, cations move through the electrolyte from the region of the negative electrode towards the region of the positive electrode. Similarly, negatively charged ions are called anions, and during the discharge process, anions move through the electrolyte from the region of the positive electrode towards the region of the negative electrode. Now, I believe it can be hard at first to remember what is a cation and what is an anion, so you will need to come up with some kind of a memory helping mechanism. And this is the one that I use in case that's helpful to use. I think of cats as being positive animals. And a cation is a positive ion. So cats and cations are positive in my mind, and anions therefore must be negative. Now, I suppose if you prefer dogs to cats, then my mechanism doesn't work for you, and you need to come up with something that will help you instead. Particles with a positive charge or a negative charge cannot simply jump from one electrode to the other. They need some kind of medium through which they can move. And this medium in a battery cell is called the electrolyte. It allows the positive ions and the negative ions to exist in a charged state inside of itself and to allow them to move back and forth through this cell. In a lead-acid battery cell, the electrolyte is sulfuric acid diluted by water. And in general, the electrolyte is some kind of solvent that contains dissolved chemicals that have balanced positive and negative charges. When the solvent that's used in the battery cell is water, then we say that the battery cell has an aqueous electrolyte. In the case of lithium-ion battery cells, we will find that it is inappropriate to use aqueous electrolytes because they just won't work, and instead we find that organic solvents are used. The chemicals that are dissolved in the solvent must dissociate into positive and negative ions. So sometimes acids are used, which tend to give off hydrogen ions with a net positive charge. Sometimes bases are used, which tend to give off hydroxide ions with a net negative charge. Or sometimes salts are used, which comprise elements or compounds with that easily dissociate into parts that have a net positive charge and a net negative charge. Another feature of the electrolyte is that while it must be a conductor of ions, what we call an ionic conductor, it also must be an electronic insulator to avoid self-discharge. That is, we don't want electrons moving from one side of the cell to the other side through the electrolyte, because then they would not go through the external circuit. So the electrolyte conducts ions from one side of the cell to the other internal to this cell, and the electrons are forced to go through a path external to this cell where they do work. The electrons do not pass through the electrolyte. Now, placed between the two electrodes is something known as the separator. The separator has the very simple function of mechanically and electrically isolating the negative and positive electrodes from each other. If the negative electrode were to come into contact with a positive electrode, then there would be an immediate short circuit where electrons from one electrode would flow into the other electrode and very quickly discharge the battery cell. Now, this separator is really a low-tech device in the sense that it is simply providing this electrical and mechanical isolation of the two sides of the battery cell. It's often made from some kind of a porous glass mat or a fibrous mat or a polyethylene or a polymer with micropores. It really only keeps the two electrodes separated from each other, but it still has pores or openings inside of it that are large enough to let the electrolyte through, and therefore so ions can flow from one side of the cell to the other with very little ionic impedance. On this slide, I also mention the function of the current collectors. If the electrode is made of some kind of metal, then we can attach the external terminal of the battery cell directly to the electrode. but often electrodes are made from some kind of a powder, and we cannot attach the external terminals of the battery directly to a powder. There's just no mechanical way to do it. So instead we attach the external terminals of the battery cell to metallic foils that are called current collectors. And the electrode powders are somehow adhered to the current collectors to allow the electrons to flow from the electrode to the current collector to the outside circuit, and then on the other side of the cell from the outside circuit to the current collector and to that electrode. In this illustration, you see that the current collector of the negative electrode is drawn as orange, and the current collector for the positive electrode is drawn as gray. And this is a convention that I will use in my illustrations, and the coloring is primarily for illustrative purposes. But it does turn out that lithium-ion battery cells have negative electrode current collectors that are almost always made from a copper foil, and copper is orange, and lithium-ion battery cells very often have positive electrode current collectors that are made from aluminum, and aluminum is kind of a silver or gray color. So even though the colors on this diagram are for illustrative purposes, they do have meaning when we apply them to lithium-ion batteries. On this slide, I present a table showing components that are used for electrodes and electrolyte in some very commonly encountered electrochemical cells. Using the lead-acid battery cell on the top row as an example, we can see that the negative electrode is made from lead, which has the chemical symbol Pb. The positive electrode is made from lead oxide, which has the chemical formula PbO2. The electrolyte is sulfuric acid, which has the chemical formula H2SO4. And finally, the nominal voltage of a lead-acid battery cell is approximately 2.1 volts. Now, as you probably know, the voltage of a battery under load is less than the voltage of a fully charged battery cell that is simply resting open circuit. So the voltage depends on many factors, including temperature, and in the case of a lead-acid battery, it also depends on the concentration of the sulfuric acid used in the electrolyte. So you will sometimes see slightly different nominal voltages listed for a lead-acid battery cell in the literature, varying from around 2.0 volts to 2.1 volts. So this value is simply a reminder of a typical or average voltage, and remember that the nominal voltage is not the exact voltage of the cell, but a representative value of what you might see when you're using that battery cell. And it's also a reminder to us that the 12-volt battery that's used in an automobile, for example, is really 6 of these 2-volt lead-acid cells wired in series internal to a package. Looking at the table, you can also see something that is commonly known as a dry cell. It has a zinc negative electrode, a manganese oxide positive electrode, and a zinc chloride electrolyte. And the nominal voltage for the cell is 1.6 volts. In a lot of applications, we can replace a dry cell with an alkaline cell, and it will still work because the nominal voltages are very similar. An alkaline cell has a zinc negative electrode and a manganese oxide positive electrode, just like a dry cell, but the electrolyte is potassium hydroxide instead of zinc chloride. This electrolyte has less ionic resistance, and so it allows higher electrical current. So we often use alkaline battery cells for high power applications, whereas dry cells might be used for low power applications. Usually dry cells or alkaline cells are not considered rechargeable. It is possible to recharge alkaline cells a few times, but this is not usually recommended, and cells must be specifically constructed to allow for this by reinforcing them so that the electrolyte does not leak out of the cell while it is being charged. One type of rechargeable battery cell that's often used as a replacement for dry cells and alkaline cells is the NiCad, or the nickel-cadmium cell. These cells have a negative electrode made from cadmium and a positive electrode made from a nickel hydroxide. Nickel-zinc batteries are similar but have a negative electrode made from zinc. You can see that they have slightly different voltage characteristics, but many applications are flexible enough to allow using any of these cells. The final table entry is very interesting. It's a zinc-air battery. In a zinc-air battery, the negative electrode is made from zinc, and the positive electrode is oxygen, which is typically scavenged or harvested from air. This can reduce the weight of the battery because we don't have to consider the positive electrode as part of the weight. Now, it does turn out that we require some structure to act as a current collector for connecting, if you will, to the air. But the zinc air battery can have quite high energy storage for a particular volume or for a particular weight, and they make very interesting rechargeable batteries because of that. So summarizing, in this lesson you've learned that the major functional components of an electrochemical battery cell consist of the negative and positive electrodes, the electrolyte, the separator, and the current collectors. The negative electrode sources electrons when discharging, and it sinks electrons when charging. The positive electrode does just the opposite. It sinks electrons on discharge and sources electrons on charge. The electrolyte provides a medium for ion transport internal to the cell in order to maintain charge balance inside of this cell. The separator prevents an internal short circuit by physically isolating the positive and negative electrodes from each other mechanically and also electrically. However, it still has micropores in it that allow for a path for ions to flow through it. Finally, the current collectors conduct electronic current from the electrodes to the cell terminals. That is, they allow electrons to flow from the electrodes to and from the external cell terminals. When we were discussing the components of a battery cell, I most often use lead-acid cells as an example. A lead-acid cell has a lead negative electrode and a lead oxide positive electrode. It uses sulfuric acid dissolved in water as the electrolyte and often has something like a glass mat used for the separator. But we also looked at a table of all the components used in some popular electrochemical cell chemistries, and you can use that table as a reference. That brings us to the end of this lesson, but moving forward from here, our next topic is going to look at how an electrochemical cell stores and releases energy.